What happens when interpretability becomes an optimization target? Quantum learning scales to all qubits, and AI infrastructure is redesigned around cost rather than raw bandwidth. In today's episode, we explore three very different but equally exciting papers: an agentic system that evolves models for both accuracy and human-readable reasoning, a provable quantum Gaussian process framework that learns complex quantum phenomena, and a fresh take on mixture of experts serving that could reshape how large models are deployed. Stay with us for a journey from smarter models to smarter systems. Let's explore the first paper, Agentic AI Models, Evolving Agentic Interpretability Tools via Auto-Research. Agentic AI Models introduces an auto-research loop that uses a coding agent, including Claude Code and Codex, to evolve scikit-learn-compatible tabular regression classes for two objectives at once: predictive RMSE and a new agent-facing interpretability score. The interpretability score is computed from 200 LLM-graded simulatability tests, split into 43 development and 157 held-out items that ask whether GPT-4o can recover feature attribution, point predictions, sensitivity, counterfactuals, structural properties, and nonlinear function behavior from a model's STR output alone. Across 65 training datasets from OpenML, TabArena, and PMLB, the search discovered 467 evolved models that extended the Pareto frontier beyond baselines such as OLS, Ridge, EBM, FIGS, Pygam, Random Forest, GBM, MLP, and TAP-PFN. For example, Hinge EBM reached normalized prediction rank 0.19 with held-out interpretability 0.71, while teacher-student rule spline reached 0.36 and 0.8. These gains generalized to held-out OpenML datasets and held-out interpretability tests, with evaluator robustness confirmed by strong score correlations against GPT-5, 4, and Claude Haiku, 4, 5 of 0.83 and 0.85. The downstream result is the most novel finding. Giving 4 ADS agents access to the evolved library improved Blade benchmark scores by 72.5% for Copilot CLI, with Gemini 2, 5 Pro, 47% for Copilot CLI, with Sonnet 4, 5, 32.3% for Claude Code, and 7.9% for Codex, outperforming prompt-only controls that emphasized iModels or Interpret ML. Qualitatively, the best models combine hidden predictive backbones with compact printed displays, often via bounded depth, sparse symbolic equations, or display-specific linearization, revealing that agent interpretability can be optimized independently of the underlying predictor. Let's explore the second paper, Provable and Scalable Quantum Gaussian Processes for Quantum Learning. This paper introduces Quantum Gaussian Processes, QGPs, a Bayesian learning framework in which the random variable is the measured expectation value, FUT equals tree, UR, OT, UO, of an unknown quantum evolution U acting on quantum states ROT. The central novelty is a provable and scalable all-qubit QGP family built from matchgate or free fermionic circuits. For observables O in the Majorana module BM, the authors prove that Har-random spin-29 matchgates induce a Gaussian process when Gaussian pairings dominate the Brouwer algebra moment expansion, with covariance kappa T equals M. O to my rho, T rho, T y nay my. Unlike earlier few-qubit QGPs, this construction scales to all n qubits because the kernel can be estimated directly with Bell basis measurements in O poly n shots when min m n m equals O1. In simulations on 5.0, qubit synthetic matchgate data, the correct kernel extrapolates accurately from 15 training points out to t equals 10, while the wrong U2n prior collapses to the mean. On a 5.0 qubit bond alternating 20xx model, QGP regression and classification recover a phase transition near J1 divided by J2 equals 1 from only one labeled point per phase, achieving 95% classification accuracy and a 0.998 latent correlation with the order parameter. For a 100 qubit XXZ phase diagram, it reconstructs magnetization plateaus from 1 or 2 training points. In Bayesian optimization, a QGP surrogate finds the global optimum in 7 evaluations on a 2D synthetic landscape and in a 5.5 qubit magnetometry task. The paper also derives a Wigner semicircle PSD correction for noisy kernels, which is more robust than eigenvalue clipping and Lambda-Dammon shifting under finite shot noise. Let's explore the third paper, Rethinking Network Topologies for a Cost-Effective Mixture of Experts, LLM, Serving. This paper argues that mixture of experts LLM serving should be optimized for throughput per cost, not raw network bandwidth, because decode time communication can often be hidden by computation. Using DeepSeek v3 as the representative workload and modeling teapot under batch sizes, context lengths, and software optimizations such as dual batch overlap, DBO, and speculative decoding, SD. The authors compare scale-up, scale-out, 3D torus, and 3D full mesh topologies with an alpha-beta communication model fitted to NVIDIA DGX H100 NCCL benchmarks and validated to within 9.6% error. The central result is that current scale-up provisioning is frequently past the cost-effectiveness sweet spot. Reducing scale-up link bandwidth alone improves throughput per cost by up to 27%, and lower-cost switchless networks outperform switch-based designs across all evaluated serving scenarios by 20.656.2%. Among them, 3D full mesh is Pareto optimal on the performance cost frontier, while torus is consistently weaker and scale-out is dominated because most MoE all-to-all traffic crosses the slower inter-server network. DBO and SD are the key enablers of this result because they shrink exposed communication time towards zero, especially at teapots of 4100 milliseconds and context length 512, making extra switch bandwidth economically wasteful. A forward-looking analysis using NVIDIA, Blackwell, and Rubin scaling projections suggests the advantage of switchless topologies will likely persist, although Rubin's faster memory bandwidth growth could eventually require software overhead reductions to preserve that lead. That's a wrap on today's AI paper highlights. Thanks for watching.